And anyways, that's where we're headed. Just wanted to remind you of kind of that difference between 102 and this class. We saw it last time, but it's probably more significant to you this time. We don't have time to go over any questions you have there on the homework. Hopefully you were able to get those answered through our MC class. That's what that's for, or you can hang on to those questions and we'll be doing it in lab here. And so we've got lab obviously this afternoon, so that'll give us another 3 hours. So with that said, I'm going to dive into chapter 3 here. I do want to finish up chapter 3, but I want you to kind of be aware of the timeline here, and I want to encourage you to get into chapter 4 as soon as you can. If you just kind of finished up, and I know it's the big Super Bowl weekend too, so chances are you probably didn't go too much past chapter 2. You're kind of happy to be done here. But if you could work into chapter 3 and then into chapter 4, the sooner the better here. And so tonight, start working on chapter 3. See if it gives you any struggles or any problems. You'll probably have a few questions, but not too many. Really, chapter 3 becomes hard when you try to apply it to the physics of chapter 4. And chapter 4 is the one that will consolidate all this stuff together. The converting of unit stuff and significant figures of chapter 1. The one-dimensional motion here that you just did in chapter 2, and then the vectors that you're learning here in chapter 3, and you put that together to do two-dimensional motion in chapter 4. And so the grand finale here is chapter 4. And if you could do chapter 4, that means you could also do chapter 2, and it also means you could do chapter 3, and it also means you can do chapter 1. So get to that point, and preferably as soon as possible, because you'll want to know if you need the time to do a little each day, think, ask questions, do a little bit, think, ask questions, and so forth. So you'll be ready for the exam. It's still a little ways off, but it's going to come really, really quick here. What is your exam date? 22nd. Okay? And so is that 2 weeks away? Yeah, so 2 weeks and 2 days. So like I said, it is a little bit of time, but even though you did chapter 2 now, you may be thinking, and I've got, the rest of this week to do chapter 3, and over the weekend I'll do chapter 3, and the next Monday I'll start to do chapter 4. And I think that's a mistake is what I'm getting at. Don't just follow that order. Get into chapter 4 as soon as you can. And who knows? Maybe you'll be one of those who have absolutely no troubles with chapter 4. That'd be great. You could just sit down, breathe through chapter 4 and say, okay, first test's gonna be just to my liking, and you're gonna be fine. So, yep. And some of you will be that way, but others of you won't. And so you need to find out if you're one of them so that you could.
Some of those long ones that you had in chapter 2 on the test?
It's a very difficult question to ask. He asked if the questions on the test will be as long as the ones in chapter 2. Obviously, in class, we're limited to the 2 hours of class time. So they can't be these monstrous problems, okay, that are really long. That just doesn't work. So many of the homework problems are much longer than can possibly be on a test. So obviously, those can't be on a test, which I think is what you're asking, okay? However, I also want to be careful here. Sometimes problems seem extremely long to students in chapter 2 because they're doing it the hard way or the long way. Okay, and it's not really like that, and so it could be a test question. So I'm not sure which one you're asking about or where you're coming from here, but so that's why it's hard to answer that. It's just like, well, that's not really a long one. You made it long because you calculated how much time did it take to go to the top. Then you calculated how much time did it fall back to the table. Then you calculated how much time it goes to the ground. That's all one constant acceleration. Just do one calculation. Why break it in 3 pieces? And many people do that. I don't know if you were one of them, but I see that, especially on the first test. We do this little projectile, and people calculate how much time did it take to get to the top. Oh, how much time did it take to fall back to the same level? How much time did it take? And then they add them all together. And they get it all right, only not to do the rest of the test because they're so busy. It's one calculation. It's all one acceleration. So that's, like I said, makes it difficult for me to answer that. All right, and then one little other bit of housekeeping. You may or may not know this, but California state law requires all teachers to be TB test four times a year, and unfortunately, they've really changed the way they do our health department. I suspect it's because of budget issues and money issues. But anyways, they're only doing the testing between 9 and 11 on Monday and Wednesday. Well, guess what I'm doing between 9 and 11 on Monday and Wednesday. So today's going to be a little different. We're going to take a break at 9:50. That's my scheduled point. So at 9:50, we'll take a little break. You can relax. 10, 15-minute break, however long it takes me. I'm going to run over there. They're going to stick me, I guess, with the pen, and I'll come back. And I guess in 2 days I'll have to go back and I'll have to look at the little stuck pen there if you know how the TB test thing worked there. So anyway, so remind me as we get to close to 9:50, we'll take a little break here. So 10, 15-minute break, and then we'll come back, and that'll be different game plan. All right, well, here's where we left off. And see if you remember it. And obviously, if you were busily working on Chapter 2, you may not here. But we were trying to teach you a mathematical technique that would allow you to deal with not only the magnitude of the vector, but the direction of the vector. Those I hats and those j hats. And by the show of hands, I asked last time, it looked like about half of you, maybe even a little more than half of you, said, oh yeah, we did this in my math class. So good. But that tells me that the other half of you haven't seen that before. But I'll just say the big picture, right? That we use our little rules of mathematics for the numbers, for the units, for the prefixes, and we talked all about those in Chapter 1. But now I add to that also for the unit vectors, okay? They have an important and useful meaning. So, this big question we were working on, remember, was this. If you are driving your car 45 miles an hour north, and you turn, and with the same speed, you turn, and so now you're going 45 miles an hour east, what is the change in your velocity? Did you change velocity? Yes, because you changed direction. You didn't change the numbers. And that's the part that is most likely new to a lot of you. How do you deal with a change where the change is direction and not the number? The number part, I know you know how to do. It's the directional part that is what this is trying to teach you. So we haven't got there yet, but we're really close to finishing up here. Here's what we did get. We said, let's say you had a vector that looked like this, okay? And this vector maybe was 4 units this way, maybe 3 units that way, which of course would be a rectangular or a Cartesian description of it. X is 4, Y is 3. We can do Pythagorean's theorem then and get a hypotenuse of 5. We could do a little trigonometry and get an angle of about 37 degrees. And so there's our 3, 4, 5 right triangles. And so that stuff I think everybody has seen before they came in here. But here's the part that was new, is then we could write the vector A, and so we put A with a little arrowhead to say it's a vector. And then we would say it is 4 units in the x direction, and that's what that little I hat means there is my review. It means how many steps in the x direction. That means I plus I plus I plus I. Take 4 steps in the x direction. And then after you do that, 4 steps in the x direction, then, so plus, take 3 more steps in the y direction. Okay, and then that's what the j hat is. So j hat plus j hat plus j hat. That's what the 3 j hat. So I go I, j, 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 right? 1, 2, 3, 4, 1, 2, 3. Okay, and so that's how we mathematically write it. And the reason for that was twofold. Number one, it created like terms that kept x's with x's and y's with y's. And that was the second reason. Why do we want to keep x's with x's and y's with y's? Well, many of you probably remember that when you toss something across the room, the horizontal components remain independent of the vertical components. And you might remember that from 102, me showing you, and I got the same equipment here today for 102, because that's where we start Chapter 4. We start with Chapter 4 to convince you that the horizontal and vertical components in two-dimensional motion remain independent. That's why we need the mathematics that will keep x's with x's and y's with y's. So, my second vector may look something like this. My second vector which maybe I will call vector B, something like this, vector B, put an arrowhead over it, and maybe that vector is at, say, 60 degrees. Oh, and then, shall I call this distance here 3, which I guess that makes that 6, which makes that, ooh, not an obvious number there. What is, whoops, oh, forgotten how to use one of these older calculators. Okay, hang on here, let's see, I guess you gotta do the angle first. So cosine of 60. Oh, I already did that side. That side's 3. I guess I already did that one in my head. All right, so I want the sine of 60. All right, 60 sine, and then times 6 equals, good. Okay, so about a 5.2. So if I've done my geometry or trigonometry right here, this is a 30, 60, 90 triangle. So if the hypotenuse is 6, you know, then the one opposite the 30 is half that, and then this is what, root 3 or something like that. But as I put these together, this is saying it's 3 over and 5.2 up. And so this is where we left on Wednesday, so I thought it would be a nice quick review to get started here. This was the point, the I-hats and the J-hats. Why? Because let's add them together now. And you can see this, hopefully you can see it pictorially, that if and I'll change colors here, but if I were to say do the total of the two, that is what is A and B, if this was your first little walk that said go I, J, 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 then do I, and then 5.2 J's. Where are you? What is your new location? What is then the resultant? R. And so your book writes it as R as the resultant. But hopefully you can see in the picture, and more importantly, you can see then in your like terms that this resulting vector is really this distance and that distance put together. It is the x component of A together with the x component of B. And nowhere did we mix a y component in with our x. And likewise, hopefully you can see it here in the picture too, is that this would be the y component of A, and this would be the y component of B. And so the resultant is the sum of those two. And that's what these like terms will do. As we go to do our addition, this is an I-hat. And I-hats can be added to I-hats, but not with J-hats in the same way that an x and a y, 5x plus 5y are not like terms. You don't put them together here. So in this case, I would have a 7 I-hat and a 8.2 J-hat as I put them together. And so that's my resulting vector. That's what happens when these two are put together. And so I get my result. Now usually we go one more step here. Usually we finish the problem with saying, well, how far is it? What is the total magnitude? And so as I said, we will use just the R without the arrow to say how far is it. If you want to just talk about its magnitude but emphasize that it's a vector, we'll sometimes do that. We'll put the R with the vector and then put the 2 bars on the side to say this is its magnitude. But in our case, it's a Pythagorean's theorem to figure out what it is, because it would be the x component squared plus the y component squared. So 7 squared plus 8.2 squared equals, and the square root of all that is about a 10.8. And so this would answer that question, how far away are you? Well, you're 10.8. And what angle are you at? Well, the angle theta, of course, let me put it in the diagram, but we're looking at this angle here, theta, what is it? And looking at my picture, I guess I would expect to be more than 37 degrees. But I can see it in terms of the tangent. A tangent would be this opposite y1, which is 8.2, and the adjacent one is 7, and so I got the inverse tangent of these. And let me just check this old calculator. The last time I forget my calculator, hopefully. Oh, there we go, degrees, all right. And so 8.2 divided by 7. Okay, and inverse tangent, 49.5 degrees here. So we can get the angle to 49.5 degrees. So, wow, just picking this one up kind of makes me wonder. Remember when those graphing calculators came out and I thought, oh, those are a pain. These are nice. Okay, amazing how you get used to it. Talking about that last night and kind of shocking my kids. What do you mean you didn't have a microwave when you grew up? And you didn't like text your friends to meet you at school? How'd you find them? Like, no, there were no cell phones, and we didn't text, and we actually turned on the oven. You see this right here? This is not just a storage place for bread. You know, you actually turned this on, and you actually cooked from it. We didn't have this one over here. Anyway, so different world. But anyways, I'm going old school today there because I forgot my calculator. But so anyways, I hope you see that idea. And like I said, if the past is any repeat here, usually students haven't struggled with the chapter 3. It's, okay, now you understand it, but now let's use it in chapter 4 where more of the struggle takes place. So one more thing, and then I'll do some examples and call it quits for the chapter and get into chapter 4. But this is adding them. How do you subtract them? How do you multiply them? So, working with directions is some new mathematics for you. And I want to emphasize, this chapter is only trying to teach you how to add and subtract. Can you multiply? Yes, you can. In fact, there's 3 ways to multiply them, and we will. We will multiply 2 of those 3 ways before the semester's over. But since we don't need it till chapter 7, I won't try to teach it till we get to chapter 7, okay? So for today, since we are going to need immediately in the next chapter how to add and subtract vectors together, that's what we're going to do. We are going to add and subtract a vector. So this is adding, and if you know how to add, you also know how to subtract. You really do here. I mean, what if I were to put this on the board? If I were to tell you, take 5 and subtract 3. Now, you probably don't think much about it. You just go, 5 minus 3 is 2. But what you're really doing and have been doing is you've been taking 5 and combining it, not 3, but the opposite of 3, the negative of 3. And if you draw a number line, of course, you see that that comes out to be 2. But my point is, addition and subtraction are really one and the same. Addition is nothing more, or excuse me, subtraction is nothing more than the addition of negative numbers, right? So let's look at these 2 vectors again. Instead of saying what is A plus B, let me write over here what is A minus B. Yeah, and so hopefully you see that first step, and you do right away. You say, well, that would be vector A added to the negative of vector B. Okay, fair enough. But begs the question then, what is the negative of B? Okay, and so follow the rules of algebra, and in this case we've got components and a distributive property. Watch this. I would write out vector A. Okay, now vector A, there's no change. That's a 4I hat plus a 3J hat. But then I'm going to add a negative B. So the negative of the whole vector B. And vector B, we just said, was a 3I hat. And was it 5.2? 5.2J hat. And as we do our distributive property then, it becomes 4I hat plus 3J hat minus 3I hat minus 5.2J hat. Fair enough? And so see how I just did the rules of algebra. So even if you had never seen this before, you could do it on your own, as I've been saying, working through these. And that's exactly the point here. And so as we work this out, again, sticking to our rules of algebra, we can put like terms together. So we put the I hats together, and so we get 1 I hat. Usually we just write that then as I hat. We don't usually write the 1 when it has a coefficient of 1. And then this one, same idea. We would take the j hats and put those together. That's a negative, that's a positive, minus 2.2 j hat, and so minus 2.2 j hat. So there's how you subtract vectors, right? You just add the negative, okay? And if you see that, then you'll be able to answer that question I've been asking you. A car going 45 miles, well, more on that in a second. Let's draw the picture though. And I'll even change some coloring up here. See if it kind of stands out here. Well, what would it look like in this picture? Now, A minus B. Well, I think you see that A would still be the same up there. So I'll just kind of draw over the top of A again. So A is still the same, but what would minus B look like? Yeah, equal in magnitude, opposite in direction. Do you see that in the picture here? This is saying the negative of B. And look at the distributive property. It is saying the negative of the x and, don't forget, the negative of the y. So instead of having a vector that goes to the right and up, I would have a vector that goes to the left and down. Both the x and the y are negative. So I just want to make sure you saw that. So the negative b vector would be 3 over and 5.2 down. It would look like that. And I know this picture's getting kind of busy up here, but can you kind of see that in there? And then the resultant, which I'll do in green, would be that. And it's probably not drawn very well to scale, because according to my numbers here, we should be 1 over and 2 down. And so I should go more down than over, and that's not really what this shows. So, but you can definitely see that it is over and it is down. It's to the right and it is down. And so I might put some angle theta. What is that angle? I might put some little r here. Say, what is the resultant? And so to finish that up and to finish the chapter here, at least before we get into examples, I might say, well, what is the resulting magnitude of the vector? Well, there's the x component 1, and I would add it to the y component, which is kind of a judgment call. Do I put the negative there or not? Since I'm squaring it, there's no point in putting it there. Although if I don't put it there, you might not see where I came from and why I changed the sign. So I'll put the negative there and then take its square root, but that's why, you know, the negative sign mathematically is not all that important. But 2.2 squared, add to it 1 squared equals square root of all that is about a 2.4. So this says the resultant is about 2.4, lengths long. And then we can come over here and look at this angle, which, again, in my picture, it's not quite drawn to scale, but that would be the inverse tangent of, and it goes down 2.2, and it goes over 1. And here again, we can beg that same question. Do you want to put the negative there or not? Certainly your choice. You saw here that if you put it here, maybe it was a little clearer in your mind. But you squared it, didn't matter. And I would say the same thing here. You can put the negative 2.2 there if you want. And if you do, you're going to get a negative angle. But isn't that what the picture's showing me anyways? I mean, I'm just drawing the angle down here. And so I'd say that the minus sign is kind of a choice on your part. What do you want? And you'll be surprised at how many times in the next chapter we don't put the negative sign. We go, you know what, let's not even mess with the negative sign. We'll just get a number. Let's get an absolute value. If we get 17, or, well, obviously this one's going to be more than 45. So, we get an angle like 50, 60, whatever. Just, we know it's down. And so we'll draw it down. We'll remember it's down. We won't worry about putting it a negative. But I'll put a negative here for question. Did I miss?
Up to A over 3 and down 5.2?
So, which vector are we talking about? A or B? You're talking about this one, aren't you?
Yeah.
So this one, which is the negative of B, should be negative 3 I hat. So 1, 2, 3, and then down 5.2. And yeah, I should have drawn it more here like that or something.
Left out the point. There's a 5 in there somewhere. Maybe you write
I know, yeah, I didn't write it. Hopefully I would have wrote it in orange.
Okay.
This 5 is from that magnitude of A. Yeah. Now I told you it was getting kind of busy, and when it gets busy like that, you can lose track of which number applies to which vector. Especially since I've got colors, and I suspect you may not have colors. Although I've seen some of your notes, maybe not this semester, because I'm just getting to know you here, but boy, last semester in particular, some students were showing me, and I kept using colors, and they had solid line, dotted line, dashed line, shaded line. I was quite impressed. I was like, wow, what you guys do? I go, I never took notes like that. I'm impressed. So, did I see another question? Yeah.
Oh, what part on the picture is the 2.2 and 1?
Okay, so I'll go to the green here. So the resulting green one is from this red one, A, plus a negative B. So this is A minus B. And so this orange one is supposed to representing the minus B. And I wanted it in the picture so you could see how B is pointing equal in magnitude but opposite to B. Now, your question is, which is this green one? It's the result of that, so we go down 2.2 and we go over 1. So the x-axis is 1. How do I know it's the x-axis? Because it's got the I hat. How do I know it's to the right? Because it's got a positive sign. This has a negative sign, so I know it's down, and it's the y direction because I got the j hat.
I'm just wondering how you get your angle with inverse tangent. If it's
Okay, so inverse tangent, if this is the angle theta, a tangent is opposite, that's this. So that's the 2.2 over adjacent. Okay, good. And again, not drawn to scale there, but I don't think that was the issue. So let me put this into my calculator. Inverse tangent of 2.2. Inverse tangent, and it looks like it's about 65.5 degrees. Now with the negative sign in it, comes out to be a negative 65.5 degrees. So you can use the negative or not use the negative, depending on what might be easier for you to think about and work with. And I probably, on something like this, it's probably easier and makes sense to leave the negative in there. That's kind of how you were taught in your math class. It's a good place to get started. But I will tell you, there are many times where I just look at it as a triangle, and it's the magnitude, 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 and then I'll look at what that angle is. Sometimes that will be better, because if you follow your pluses and minuses exactly like you learned in a math class, then that only gives you the angle as measured from the x-axis, as you learned in your math class. And we don't always want that. Sometimes we want the vertical axis, and so we want to mix things around a little bit. So we want to make sure we understand our trig function. Okay, good. I think we're there now. Final question. First question was the answer here. Can you help me now? 45 miles an hour north. Continue to go 45 miles an hour, but make a turn, and now I'm going east at 45 miles an hour. What is my change in velocity? So, here's my grid. My x-axis course, I did it in terms of a compass road, so let's call this north and east. Never eat soggy waffles, okay? So northeast, south, and west. All right, and so I'm going to go north first. So how would I mathematically represent my initial velocity vector? And since I'm talking about what am I initially doing before I turn, let me not call it A or B anymore here. Let me put a V, put an I, initial velocity, arrow, vector. What direction am I heading? How would I mathematically describe this one? Yeah, I guess it would be 45. And let me drop the miles per hour. I know I said miles per hour, but just remember it's miles per hour. But as I heard somebody say, it's J hat. Now, if you want to put 0 I hat, I suppose you are more than welcome. But we don't usually do that in a math class. We don't usually put 0x plus 5y. We just have 5y. So I, guess I'll put it here so that it's very clear to you. There's nothing in the x direction. It's all in the y direction. So there's our new piece of mathematics. Now, where's the other vector? Well, the other vector would be, say, our final velocity, right? How would that fit on here? Well, I guess I would say there is final velocity. And what do we say the final velocity is? Well, 45. And I'll drop the miles per hour which direction? Okay, so it's east, so that's the I hat direction. Good. So there's the I hat. So, and again, we'll put a 0 J hat this first time here, but hopefully you see it's not, a necessity. It's just that's what we have there. All right, so the question is, what is my change in velocity? And this is why I had to show you both addition and subtraction. How do you get a change in something? Final minus initial, right? Where did you finish at minus what did you begin at? That's your change. So I would write this out as final velocity minus initial velocity. And I'm hoping you'll be amazed by the end of this chapter now that you said, wow, I can do a numerical calculation for the change in velocity when its speed didn't change. It went 45, 45, 45, 45 the whole time, but it changed direction. And then there's a number and a direction associated with that change. Exactly. All right. And so let's see what it comes out to be here. So final would be 45 in the I hat direction. Initial would be 45 in the J hat direction. And maybe I picked one that was too easy. There's no I hats and J hats for the two to match. So you're done, right? Put I's with I's. There are no other I's. It's just 45 I hats. Put J's with J's. Well, there is no other J. So you've got 45 J hat. How do you get the magnitude velocity vector? I guess it's 45 squared plus a negative 45 squared. Square root. There it is. That's the magnitude of the change in velocity vector. Now we have a way to figure out what that change is. And so that should be 45 times the square root of 2, which is about a 63.6. So 63.6 for the change. And so some of you saw it at the very beginning, but I'm hoping at least one of you didn't, so this was worth our time together to say, wow, that's how you calculate change in 45. Now, we should still talk more about this, because I think it takes a little while to get a gut feeling. We should draw some pictures here, but that's the change in velocity. 63, wow, 45, change 63. Like I said, I wouldn't have guessed that until we start looking at some pictures. Then maybe I would guess it, yeah?
Yeah.
Well, it'd be miles per hour. Sorry. So all of this was miles per hour, miles per hour, miles per hour, and we're back to a question: do you or do you not put in the units? And sometimes you do. Probably best if most of you do, but as I said, as we graduate now from a lower level to what I call post-calculus, so pre-calculus stuff, we love to put in the units. Important post-calculus, we don't want to ever forget them. We don't want to say that they're not important, but the truth is we're going to do so many involved things in terms of Pythagorean theorems, integration, that the units make it messier than better. So we kind of keep track of them in our head. But maybe you're not there yet. So we'll just leave them alone and leave the units in.
I'm not understanding your arrows. Didn't you say you were going north, then turn east?
Yeah.
So why do you start from the origin to go east?
Well, okay, good. I'm glad you asked. I want to look closer at this picture. Look how I drew the picture. I could draw it in a number of different ways. And that is one way. In other words, that picture that I have there is what? Well, it's a picture that is saying the direction of the velocity, not the position. See, if I had told you that I went 45 miles, then I went 45 more miles, I could see how you would say, why don't you put this vector here? Because you are saying after you go 45 you turn. But does this plot represent distance, position? No. So 45 to the east is any line that goes like this. Where I put it becomes immaterial, because that graph does not represent a position. And that can get a little confusing, I know, because some graphs are plotting position. This one is not. This one is plotting the direction of the velocity. So where I plot it really is irrelevant. And for those of you maybe even done your vectors in your math class, that's often a question I'll get, say, hey, Dr. Young, I've been doing these vectors in our math class. I don't get it. And the teacher's just putting it anywhere he wants. Right. Because what are you plotting? So sometimes you do plot distance, and there you have to put it in terms of distance. But this is not a plot of distance, and hence I'm only trying to plot what direction is it. So I'll put it wherever it's convenient. So you've asked a good one here. You've asked, okay, here's that first one, which you had no problem with, 45. It's initial velocity, and it is a vector, and so it was in the j-hat direction. And in that picture, and let me just repeat it so we can kind of study the two together, I put then final at 45, and I put it in the i-hat direction. And that was certainly one way of looking at it, but also, of course, I could put this, which would be initial, so there's 45 in the j-hat direction, but I could have placed the vector right here. It sounds like you kind of got my first step. My first step is either one would represent the same thing. Here, here, and here would represent the same thing. Although I would say putting him over here does me no good, does me no advantage. But I would say there is good reasons to look at it this way. And there are good reasons to look at it this way. So you want to take your pick while you're doing the homework and say, well, which way am I going to draw it? Which way is more convenient? Which way portrays more information to me? Okay, let's take a look at this one. This is what I had been doing most of the lecture, right? Drawing them head to tail, head to tail, head to tail. Why? Well, what's this right here? From the beginning of the first to the end of the second one. What would that represent? Yeah, the sum of two. And I wouldn't say displacement because these aren't disposition vectors. But I would say that this is the sum of the two. This is initial velocity plus final velocity. So when you draw them head to tail, you see the sum of the two vectors really well. And until these last 10 minutes or so ago, I was always doing addition. And hence I was always drawing them this way. So without really explaining what I was doing, I was drawing them in the picture that looked best for addition. And so I would say this looks really nice for addition. Sure. In fact, I'll take you one step further. That what if you were to draw final velocity first and then initial? Don't you get the same thing? And for any of you who've done this in your math class, you call this, oh, how are we doing time? Oh, good. For any of you who've done this in your math class, this is the parallelogram method. You can draw either of the vectors first. And the arrow down the diagonal is the sum of the two.
That's only for tail to tail, right?
Hang on with that. Okay? Because I guess what I'm trying to see is this parallelogram is really nice. Diagonal shows me the sum of the two. What about the other diagonal? And maybe I'll change the colors. Yeah, now this one's at right angle, so, you know, maybe I should have labeled this, but I didn't want to do one off angle quite yet. But if I had one like that, right? Well, this down the middle is the sum, but what's this across that's middle? The other diagonal. Shall I just put a question mark here for a second and kind of analyze it? I mean, this from here to here would be initial vector, right? Plus this diagonal, which I'm trying to figure out what it represents. When you go from here to here, you end up with this one, don't you? Which is final. And so if you bring initial to the other side, I want you to see something interesting here. And I heard a couple people say it. The other diagonal shows the difference between them. So the little parallelogram is a nice visual tool of one diagonal is the sum of the two, the other diagonal is the difference. Okay? Now notice the one that gives me the difference, it's easier to see the diagonal if I put them tail end to begin with, right? So what have I been doing? So as soon as we went over to subtraction, without even really thinking about it, only because I've done it so many times, is I drew them tail end to tail end. Because I know that from here to here is the difference. Okay. So if you haven't seen that before, it's really nice. Take two vectors, draw them, and then maybe draw them in reverse order down below so you get a little parallelogram. The sum of the two is one diagonal. The other diagonal is the difference between those two. And so you're going to look at whichever one you want. You can look at them head to tail, or head to tail in the other order, or you can look at them tail end to tail end. You know, whatever's nice. Whatever gives you the most information. Usually in subtraction, tail to tail gives us the most information. And head to tail for addition. But, you know, there's exceptions to that, so.
For position, would you do tail to tail? Like position, a position graph?
Are you adding them? Are you subtracting them? Yeah. So, no, I guess the answer still goes back to, am I adding them or are I subtracting them? Yeah. And I would do it the same way. Yeah. Yeah. In fact, now maybe you can begin to see this. Remember the calculation that we did. This was the question. If you go 45 miles an hour north and turn and become 45 miles an hour east, what's the change? 63. Do you see it now in this picture? What's 63? That diagonal. 63.6. That's 45, that's 45, that's the 63. So that's where it came from. You're basically going like this, and you're losing 45 this way, and you're gaining 45 that way. But that doesn't come out to be 90, right? In the same way as 3 this way and 4 this way doesn't come out to be 7, does it? They're at right angles. And so we've got to go 45. We lose 45 this way, we gain 45 that way, and it's right angled. So we draw the hypotenuse and we get our 63. And if you saw that picture from day one, then good. And obviously some of you did, because when I first asked this question last Wednesday, I heard somebody say, well, it's 45 times the square root of 2. And that probably was meaning you had that picture in your mind. Yeah.
So, is that, when you throw in the direction, does that mean you're going 63.6 miles per hour in the south? east?
Oh, no, this is not it. Well, wait a minute. Okay. I think you got two things mixed up here. This is not a speed I'm ever going. I'm not going 63 miles an hour, right? I'm going 45 in one direction. I turn a little bit. I'm going 45 in another direction. I turn a little more. I'm going 45, going 45, going 45. You know, I'm always going the speed of 45. This 63 does not represent a speed. This represents a change in the speed. It might be like having $100 and paying a $10 lunch bill, and now you have $90. Well, your change was $10, right? Did you ever have $10? No, you went from 100, and you might say, I went from 100 down to 99, 98, 97. I never had just $10. I always had a lot more than $10. Fair enough? So your change is not how much you have. So I was never going 63. Okay? Now, you said something about direction, though, that I want to keep going with here. There is a direction here associated with the change. And we can calculate that one, couldn't we? I mean, we could go through some mathematics here. We probably don't have to do too much, and in the interest of time, I won't even bother, but I bet you could tell me this angle right here. Or maybe this angle, at least one of those. Yeah, they're each 45, right? 45 degrees, 45 degrees. Right? Inverse tangent of 45 over 45. Inverse tangent of 1, 45 degrees. So there's my angle of 45 degrees. So what you are saying is the change in velocity also has a direction. It's 45 degrees down. Put over in this graph and drawn in blue, this was here, this was here. Now in this picture I've drawn it across here, but let me take that same vector and put it here. There's my change. So my change is kind of a southeast direction, isn't it? And hopefully that kind of makes sense, southeast, because I am going north. So if I have a change to the south, that would stop my northern movement. And then having a change to the east would speed me up to the east. And so my change is a southeast direction. I was never going south, though. My change. Right. So be careful. And as we'll see here, and you probably already know from the last chapter, the change in velocity is going to be called the acceleration here. So I'm going to have a direction for my acceleration vector. And sure enough, that is it. All right, well, I said we'd take a break here. I think this would be a good time. I'm going to run over there. You guys take. Hopefully it won't be too long here, but stretch your legs, use the restroom.